In this video, we'll see how to calculate an entropy change for a chemical reaction under constant pressure conditions. And I'm going to put that in small print there because almost always in the lab, we're under conditions of constant pressure. And you might say, well, what do you mean by that? Well, I mean that the reaction is done open to the air. And so the air pressure pushing down on the reaction is constant. And that is different from a constant volume reaction. Imagine you did a reaction inside of a bottle with the top on, then any gas that builds up or is made in the reaction will increase the pressure inside the bottle but won't change the volume. So we're looking at constant pressure reactions, reactions open to the air. All right, if you remember when you're under conditions of constant pressure, the change in enthalpy of the reaction is equal to the heat of the reaction. So that allows us to go ahead and write the statement we saw earlier. So delta S for the reaction is Q for the reaction over T for the reaction. We'll just assume that the temperature is the same throughout. And we can say that is equal to delta H over T. In fact, we will deal with the reaction so often, we'll just write delta H over T instead. So we can say delta S for the reaction is equal to delta H for the reaction over the temperature for the reaction. And we have to remember, whenever we don't write these little things here that says reaction and reaction and reaction, we are so reaction-centric in chemistry. You just have to remember that. If we don't say, we're referring to the chemical reaction. All right, let's go ahead and apply this now. So let's say we've got 25 grams of water. And it freezes at 0 degrees C. And we know that the enthalpy of freezing, or the enthalpy of fusion, is equal to positive 6.02 kilojoules per mole. So just a reminder here, right? This little symbol here means we're under standard conditions, so the water is pure, and we're under a pressure of 1 atmosphere. We can use this to calculate delta S for the reaction. So we can go ahead and we can calculate delta S. And again, remember, if we don't write the little subscript here, we're on about the reaction itself. All right, how are we going to do that? Well, let's go ahead and pull up another slide and go through it together. So the first thing to remember is we're given delta H of fusion, but we are trying to find delta S for the freezing reaction. And what is the fusion reaction? Well, fusion is melting. So melting is actually not the same thing as freezing, right? It's the same thing. It's just done backwards in time or done backwards in reactants and products. So this, right, we were told earlier is equal to positive 6.02 kilojoules. Remember, right, when we melt, we break into molecular forces. So now if we want to freeze, we have got to flip it around. So we got to go ahead and we got to take liquid water and change it into solid water. So we are reversing the reaction. And when we reverse a reaction, we reverse the sign of the enthalpy change. Okay, remember with equilibrium constants, we invert them because reactants and products swap sides. But for enthalpy, right, we are changing the sign. So if heat goes in one direction, it has to go in the other direction. What goes up must come down. Alrighty, so now we got 25 grams of water. So we have to convert that to moles because it is on a molar basis when we write a thermochemical equation. So we add up the weights of hydrogen and oxygen, we get something like 18.02 grams. So we set up this conversion, right? So 18.02 grams is a mole. So, okay, we could stop there, but we can also calculate delta H. We could calculate Q. We know that the way to read the thermochemical equation is whatever that coefficient is the number of moles, and the number of kilojoules. So we can calculate delta H. So it is minus 6.02 kilojoules per mole of water. All right, and I get minus 8.35 kilojoules, and that is the entropy change. And remember, for a chemical reaction, that's the same thing as Q. All right, I could also write it in terms of joules. I remember that a kilojoule is 1,000 joules, so that is minus 8,350 kilojoules, with the 2 just being a guard. I'm sorry, did I say kilojoules? What an idiot. I meant joules. There we go, much better. We can calculate delta S now. So delta S is Q over T. So now we got Q, so it's minus 83.52 joules. The temperature, it was 0 degrees C. That is 273.15 Kelvin. And we go ahead and we can see the whole thing must be negative. In terms of significant figures, we are only allowed to write 3. So it would be minus 30.6 joules per Kelvin. So when we freeze water, we decrease the entropy of the system by 30.6 joules per Kelvin. So there's fewer microstates possible. Oh, I said I wasn't going to mention microstates. So there's more order, if you like. So the water crystal, right, the molecules are arranged in a rigid, fixed array that is more ordered than the liquid water is. So we've reduced the entropy of the reaction itself. Now, if you've been paying attention now, you think, aha, I've caught Dr. Napper in a trap, right? He said that's not possible, right? You can't lower the entropy. Well, actually, I said you can't lower the entropy of the universe. Now, the universe is made up of a system and the surroundings. So if the system, or the reaction, if you prefer, goes down in entropy, that's okay as long as the surrounding goes up in entropy by a larger amount than it went down. So we're allowed to increase the order in a region of the universe as long as we increase the disorder by a larger amount in a different region. And that'll bring us on to another lecture. So pause that thought and hold it. Congratulations if it came to you, and let's see how we can get out of this conundrum.